Okay, so James Dent is a professor at Sam Houston State University. His work spans cosmology, dark matter, and gravitational waves. He was previously at Southwestern Louisiana University and was a postdoc at Arizona State University and Vanderbilt University. And he is answering the question, what is mathematics to a physics student?
Yeah, thank you. Thank you so much to the organizers. Although after the first two talks this morning, I don't know how much I can thank them having to follow these two fantastic speakers. So thanks a lot. Yeah. I do have actually both talks on my shirt here. I'm in diagrams on dark matter, right? So that's good. Right, so I'm going to answer this question in maybe a little bit of a different way. I'm going to try to, I think, bridge a little bit of the connection from where all of you hand off the students to us, and then we get them to become the Rachels or Grants of the world, maybe, right? So I'm not going to go through, the beauty of high-level mathematics so much as what it means for us at the teaching level, the undergraduate level, right? And how do we get them to understand things from a more mature, physicist perspective. So this quote comes from Julian Schwinger. This was in his 1965 Nobel Prize lecture that he gave. But I'm really going to be talking about this today, which is that math is often a barrier to the physics success for many of our students, right? And this quote comes from, well, a whole lot of people. So I will say some things that are definitely, idiosyncratic to myself and our university, but I do have collaborators around the country, and we see a lot of similar things, right? So Nick just told you essentially about the kind of things I do. So sort of half my job in research. I do dark matter, cosmology, gravitational waves, and general beyond standard model physics. However, a lot of the other portion of my job is this. And it has been, nice at this stage of my career. I've gotten to teach through pretty much the entire undergraduate curriculum from the very beginning, Halliday and Resnick style, all the way up through, general relativity and math methods courses sort of at the, entering graduate level, right? So one has a little bit of a perspective at this stage of the career. So this is where I'm really going to be coming from today. Right? There are certain expectations we'd like to have, and this is a very beautiful quote here from Professor Sarfati. And it would be nice for our students to come in and have a certain amount of mathematical sophistication so we can, just get to the physics right away. This would be a wonderful thing for us. So for our expectations coming in to say physics 1, just classical mechanics at the calculus level, we want them to have calculus, of course. And this is built on a foundation of other things, trigonometry, geometry, and algebra, right? And of course, we know the usefulness of these things. This is just a plot sort of from the first semester course in physics, right? We need to understand kinematics and dynamics. We need some trig and geometries. We want to talk about vectors. And we like to talk about extended objects, so maybe a little bit of integration and higher dimensions and everything. So this would be sort of an idealized version of our students. They would be able to understand all of this. And right away, they come in knowing all the mathematics, so I can tell them about all this physics. However, there's sometimes some misconceptions about mathematics, let's say, which is, I think, encapsulated in this quote. So yeah, I see from none of you are aware of this, it seems to. Right. So this is what we actually see, right? This is what we know and what we see. So in calculus, where I am, so I'm at an R2 university, so it's high research, but not R1. So we have more teaching for us. Our students come from different backgrounds, certainly. But we have students who have not all of them even had calculus, right? And the ones that have had calculus, I have plenty of students who have had AP calculus and they've done well in the AP tests, but they come in what I'd characterize as being sort of algorithmically rich and conceptually poor. Sometimes even just, hey, I give you a derivative with respect to x, and they can do it like Mathematica, right? It's great. Now it's x of t. I want a velocity, wait, I take derivatives with respect to x. Right? What are you talking about? It's like they walk in the door of the physics class and suddenly their calculus has drained from their minds, right? So, yes. Trigonometry, similarly, a lot of them may be able to tell you something about ratios of sides of triangles. They may be terrified of trig identities and they think that that's where the real, magic is somehow. But they don't necessarily have a good foundations of, say, periodic functions, which is what we need. those kind of things, right? Geometry, similarly, there's often the lack of connection there. They might have done some proofs and so forth. And geometry, I'm even including, plotting algebraic functions, for example, and understanding that. Because a lot of what I do is making a figure, right? That's the thing. If I'm going to do a shorthand, read through a paper that might have interested me, I'll go and look at the figure. That's so much condensed information right there. So that's the kind of thing we want them to do. Algebra, there's some memorization and quotes, as you probably all know. Sometimes folks do not know what they think they do. I'm included in that, of course. There's over-reliance often on mnemonics and calculators. I don't know if you've ever had the experience of arguing with the calculator, where they will hold it up and say, but my calculator says. And I'll say, that's because it knows the order of operations and you do not. Or my high school physics teacher said, and I say, I promise you, she did not tell you the energy is not conserved here, right? These kind of things. Okay. So then what are we doing about it? So what I'll talk about is what we're doing locally, and hopefully we're going to have a broader reach with what I'm going to tell you here as well, a program that we've developed over time. And that is what we call a physics boot camp. So this is an early intervention, typically first semester or second semester, something I'm teaching right now, actually. And what it is, it's before they go into, say, their calculus-based physics courses. We're trying to get them up to speed on, they need to walk in, they're calculus ready, they can understand the physics now, right? They can, or study the physics. So this was developed by my friend Joel Walker, who's a colleague of mine at Sam Houston State over a decade ago. I've been teaching it for 8 years. This is actually a picture I took last week from my class. So there's 3 hours of lecture each week, and we have 2 hours essentially of drills, and that's what you see here. So we have this very nice active learning component. I have a couple of TAs you can see here, and the 3 of us walk around the room. There's a lot of peer instruction as well in this. So our goals here are we want to introduce the field of physics, right? But we also want to increase math readiness. Because not everyone is going to go on, of course, and become a theoretical physicist. A lot of our students will go into, say, engineering adjacent things. A lot of people go into various types of coding as well, different technical jobs, right? But our goal is getting into the mathematics that we need as physicists, because we have different priorities than the mathematicians do, right? It's not that we're not interested in math, we are. I mean, that's the tools that we use, as professional physicists, of course. And we also get into this wide range of topics. I'll give you a taste of that here in a second. As I mentioned, we do a lot of active learning in my class, a lot of peer tutoring. But what we try to get into is exposure to thinking like a physicist. So we go through this algebra, geometry, trig, and all these things, and we really try to infuse it with, I can see the finish line, right? At the end, how do I go from this trig and these, a mass on a spring to talking about quantum field theory, right? So we really try to bridge that gap. Another thing we've done is we have had a summer course, which was extraordinarily intensive in 2023. We did essentially a whole semester in about 9 days. We had a really good group of students. This allowed them to kind of shortcut some prerequisites, which definitely our students appreciate to save a lot of money. So we have been really trying to implement this, broadly. Okay. Another thing we have, and I'm not here as a salesman, well, not only as a salesman, but we do have a textbook. So my friend Joel Walker and I are writing this. It's being published by Cambridge University Press. Should come out next year. I will tell you how to get a copy of this for free a little bit later. Okay, so I'll give you some swag here. And you see our cover image here is a proof of the Pythagorean theorem, right? That Joel actually painted. Very nice. So let's take one step back, and I'm going to kind of reset what our expectations are now, thinking about it within this framework of our physics boot camp, but also getting them, with a mind towards how do we get them to think more like a physicist and actually to have success in their upper level classes, right? So we take a step back into thinking about arithmetic, algebra, trigonometry within this physics perspective. By the end of the semester, we actually introduce calculus. So the last few weeks of our class, we'll do derivatives and integrals, right? So I'd like to think of this as we go literally from counting to calculus in one semester. Okay, so where do we start? We literally start at the beginning, and we talk about counting. I wrote down actually all the things that were used in Grant's talk earlier, and these are on the board. I had no knowledge of what he was going to show the details of, but you saw these kind of words already, permutations and so forth. Of course, probabilities are operations and so forth. We saw a lot of dimensional analysis. So we teach these things, right? And we try to get them also a little bit of the vocabulary in a safe sort of, a safe framework. They understand, of course, how to add and all these things, but they might not know, say, the generalization and abstraction that we need from them, or some of the terms you'll see, like an inverse. We start that right away. Subtraction is an additive inverse. We have multiplication, division is inverses. And then we can go all the way through, derivatives and integrals are inverses, inverse matrices and so forth. So we sort of cycle through these kind of things at ever increasing levels of complexity is sort of a part of our philosophy, right? So just as an example, these are some of the things that I give the students in the first week of class. A lot of these things is, yes, we know how to count. We don't sit around and count pencils in the room, but you will end up with things like, in quantum mechanics, you have to count, say, atomic levels. You want permutations. This is sort of the beginning of statistical mechanics. We deal with combinations. And I put this down here because in a research meeting, actually a week ago, we were talking about looking at high-energy neutrinos from evaporation of primordial black holes. And a question came up from one of the grad students at another university I was working with, said, well, how many parameters are there? We have to sit and count an n by n matrix that's unitary and so forth. And so we're not just counting, but it's counting with constraints, for example. Right? So these things come up over and over in your career, and we actually put some of these kind of problems in there. They don't know the derivations of everything, but we try to get them comfortable within this physics environment the way, we like to think about things, right? So again, some of this kind of stuff. Our operations, scaling, you're looking at a chirp mass, which gives you some idea about, say, the amplitude of a gravitational wave. They may not know all the physics of these things, but we're asking them to do algebra, to do mathematical abstraction, to look at scales, which we just saw a whole lot of from Nick, right, within a physics context. And so we're sort of revisiting these fundamentals of mathematics, get them thinking the way we like to think about. And again, one of the main key things for us is abstraction, right, doing the math without the numbers. So, also, I had not seen Grant's talk earlier, but, very clearly, this is the case. So I'm going to walk you through the simple harmonic oscillator. How do we get from, talking about triangles to being able to do quantum field theory? And there's some joke here about, from my perspective, the career of an old phenomenologist consists of, abusing this quote repeatedly in all the classes I teach. But, all right, so this is just, and if you like these figures, this is from our text. So let me just show you how, one pathway, something that we'll come back through, and this kind of goes through the first semester of this class I was talking about, right? So we can start with right triangles, and, what's the question though? What's any of this good for, right? Why do I need to know this stuff, right? And say, well, there's this pathway where we start with triangles, and we end up talking about quantum field theory as, the oscillators are our prototype example here, right? So why do we need right triangles? One thing is we want to talk about vectors, right? And then we talk about triangles that are not all right, and we'd like to talk about circular motion. So we end up saying, well, what in the world do triangles have to do with circles? Well, here it is. I can describe this motion of my position, velocity, and acceleration using these trigonometric functions. So we go from the ratios of sides to actually periodic functions. Once we have periodic functions, we can describe waves. We decided to put an apple on a spring here, let it go back and forth, right? So these kind of things you've probably seen is now we have trigonometry, we have geometry, and we're discussing vectors, right? So we have position, velocity, acceleration. We can discuss circular motion. It's, of course, exactly the same kind of mathematics that you'll see once you do put a mass on a spring, right? So then we have this notion of these oscillatory functions, okay? So then we can go a little bit deeper and say, well, there's this thing called a boundary condition, because I have these two possible periodic functions that are solutions, but I just have this one mass moving back and forth, right? So what's going on here? It's like, well, if I set this problem up in a certain way, right, I have a certain boundary that I'm setting, right, this allows me then to fix some of these constants, for example, and we'll see these boundary conditions show up later and later as you go on through your undergraduate and graduate coursework, of course, at ever increasing levels of sophistication. So then we can talk about velocities, right? So I have another boundary here that, yes, the sign vanishes at t equals 0, so this is setting, what my velocity is, the type of oscillatory function. And then we can say, well, this can be applied in other guises. And we heard about the pendulum briefly earlier. Okay? So then once they have derivatives, we come back to this. Again, this will be sort of the end of this semester that I'm teaching right now. We're sort of doing the quadratic equation right now. And we'll talk about, I'll sneak differential equations into this by the end. Because this just is a question, right? This is a sentence. It says something. It says, I am a function, x. And if you take my derivative twice, you get me back with a minus sign and maybe some constant. And by this time, hopefully, they know, well, there are some things I know that do exactly that, right? So then I can try this solution. I can take a couple derivatives, and then this is going to fix, some of my constants here, right? And again, we can go and employ our boundary conditions. So now they're seeing them in a little bit more sophisticated scenario, okay? And we can fix our position through this. What if I want to do this without time? Well, it's exactly the same equation, right? So this is another thing we try to get them to see is, a lot of times, well, our joke in the Newtonian mechanics is, there's just one problem. It's just one problem. It's F equals ma, right? It's the only thing. So you can do the same thing with derivatives. This looks exactly the same as this equation, right? So, well, it's t's and x's. That doesn't matter. We know how to solve this thing now, right? So we can go through and do the same thing, and maybe we want to fix our boundary conditions at two different points in space. Well, this is something we call a standing wave, right? And that's exactly what you're going to see whenever you do quantum mechanics. The particle in the box was mentioned earlier. So once they can do this, right, then they'll get into their quantum mechanics class and they can get to worry about wave-particle duality and all that, but they don't have to worry about solving this differential equation. They know how to do it, right? So we're sort of offloading a lot of these, conceptual difficulties, which are many, for me too, dealing with different, physics. We don't have to worry about the math so much, right? And then we come back to trig in another way, okay? And one thing we're very fond of is horrible jokes like this. Our editor actually said, could you please cut down on the dad jokes in the book? I said, I don't know what you're talking about. And all these Empire Strikes Back references. So we'll walk them through complex exponentials as well. And this also gets to another question of, well, what's this good for? These complex numbers. And again, we saw these e to the i's all over the place when talking about quantum field theory earlier. So this, of course, is a wonderful formula, Euler's formula here. And yeah, I like to go through and show them fun things like where are the other cube roots of 8, for example. But then we can go through and say, yeah, we can actually turn these things into the trigonometric functions themselves. And guess what? We can go back to the equation that we just looked at. And now we have these complex exponentials, which give us solutions. And our favorite way of writing waves in E&M actually uses these kind of complex exponentials. So early on, we're able to get them to hopefully start thinking about this mathematics. It's going to come back later on in their physics courses, right? And it goes on and on, right? So why is the harmonic oscillator of interest? It was said earlier. If you look at the Taylor expansion, right? If I expand around some minimum point, then naturally you're going to get this sort of x squared kind of potential. So we can look at potentials like this, even in the context of just, I want to look at linear functions and then quadratic functions, and now we want to go to polynomials, and now I want to look at things of x to some power, right? X to any power, positive or negative. And now we can look at things like vertical and horizontal asymptotes. So we can just have some kind of scaling relations and say, well, how does this thing look as x goes towards 0? How does it look when x goes to infinity? And we can write functions down like this. Well, it turns out things like this, of course, dictate, orbital mechanics, for example. So you're going to see this later on in your, advanced classical mechanics classes and so forth. And then in quantum mechanics, literally Grant drew this on the board earlier, these things. Harmonic oscillator potentials are there. Statistical mechanics, you'll do something like calculate partition functions for the harmonic oscillators. Right? So we see these kind of things showing up over and over and over. It's not the only thing, but it's a good example, I think. So this is kind of the philosophy that we have in the way that we're teaching these things. And again, we really start going back to the basics. We do drive hard. It's very intensive what we do. Certainly we ask a lot of our students, but they do respond, right? And then as you go on, of course, throughout your courses, you get to see a lot of other things. A lot of these are actually written down today as well. You're going to see, other courses in the physics major. You get into vector calculus, your Maxwell equations without the axion piece on there. Linear algebra, of course, is very important for all sorts of things, quantum mechanics, for example. Differential equations, ordinary and partial, we've seen a lot of those today. Complex analysis, as well as I mentioned, calculus of variation, so looking at actions and so forth. The tensor analyses, doing general relativity, for example, probability and statistics, and And of course, all this also tends to get wrapped into looking at numerical things as well, because one of the things our students are able to do, they are able to access research, is usually at the numerical or computational level. So undergrads typically are able to help us out with things there, as I'll mention in just a second. So this kind of takes you then from, if you think about the scattering diagram that was shown earlier, the asymptotic negative infinity is them in high school. They come and interact, stuff happens with us, and then we send them out afterwards. Right? So here's the stuff that happens. Okay. So let me just briefly tell you about my place. So we do have, I think, some notion that this stuff is working. We have a lot of undergraduate students who do research with us. And what you're seeing here is pictures of some of our students at the PHENO conference at the University of Pittsburgh that's held every May. We usually have a large contingent, and all these students have done research projects with folks, right? So I'll just point out a few folks here. This guy right here is Justin Ward. He's a student of mine. He's working with me doing gravitational waves from first-order phase transitions in the early universe. So what he's able to do is he and I, and a couple other students, we're working through some general relativity now, but he's able to participate he does a lot of the numerical work in this, right? So he's working with me and Jason Kumar at the University of Hawaii, for example. So yes, we have students who come from, not always, these are not students who had all the possible opportunities that you could, let's say in high school. But we're able to bring them from places that are in that, maybe not have had calculus, get them through the boot camp course, get them into the major, get them some experience with research, and some of them have gone on, and we will continue to produce students who go on to, graduate school in physics, places that you know of, I'll say. And just a little bit indulgent, I mentioned that we have some non-traditional students here. I'll say something that may make your day is if you want to go and read about, this will be online. This gentleman right here, James Floyd, is a very interesting student of ours. He did not go to college straight out of high school. He went to the Navy when he was 18 in 1964, and he came back to school at the age of 71. And he started in our boot camp course. And what this is a link to is if you go and click on this link, there's an interview with him in Physics Today magazine. And so he graduated at the age of 75. He was in a few classes of mine. He's been a TA of mine. He's actually helping as a teaching assistant now in our department, and he does research with we have two professors who work on collider physics, and he's helping out with them. So we have an extraordinary range of students. I'm very proud of them, so I wanted to mention it. So here, back to this. If you'd like to get a draft copy of our texts, email me. I'll send it to you. I talked to our editor. He said, I trust that high school teachers will be honest and not put this out on the internet. So he said, you meant high school teachers? Yeah. So if anyone wants to look through any of this, even if you would just, hey, there's some problems here I want to take and give to my students, that'd be great. Any feedback that you could give us would be greatly appreciated. The principal writing is about 90% of the way done or so, I'd say. And also, I would like to take a moment just to say, since I am here, both Joel and I have really, we have a big debt of gratitude to the KITP because we're at a more teaching-intensive university, and they have a program here that's has allowed us to come and spend some time, and we have sort of a foot in both the teaching and the research worlds, right? And a lot of this book has actually been written on the Munger deck over there. Last summer I did a lot there, and we've had a lot of discussions from here. So it's played a really integral role, and it's a special place for us. So I'll leave you with Schwinger's quote again and say thanks.
Thanks for the fabulous talk. Are there any questions for James? I'm seeing quite a few. Maybe I can hand you my microphone.
Hi, I'm very excited for your textbook, so thank you. But your hopes, I guess, for implementation for the textbook, is it more college level, or are you looking at high school level?
It could be either. One other sort of biographical note I didn't put on there is I live with someone who's taking AP Physics right now. I have a daughter who's, she's been one of our editors as well. And so some feedback we got when we were first talking to Cambridge about this was from AP teachers, and some said that, of course, I understand also about the curriculum restrictions and how you don't just have time to do whatever you want. Right? Someone said they thought it might be a good companion for before the Physics C, something like that, or just as a supplement there. So it could be for dedicated high school students, but also kind of first year university students as well. We've had some discussions briefly with maybe some two-year colleges.
Or even just advanced math, like in the math department versus the physics department.
Well, we sort of end at calculus is where our book ends. Yeah, so, yeah.
All right, more questions?
Thank you. I guess I have a twofold question about physics education at the high school. Maybe 25, 30 years ago, there was an initiative to start physics first, where they teach physics in the 9th grade, and then they study chemistry and biology, and then they go on to do AP physics and any of the other AP sciences later in the high school. So I just wanted to know what you thought of the way the physics curriculum is structured in the high school. And then my second part of the question is, what types of students are naturally successful in a physics course, in a freshman physics course in college?
So the second one first, a lot of it is the dedicated students, certainly. The students I see who come to my office hours or who are setting up study groups with others and all that. And this is something I definitely push a lot. It's really the repetitive, work that will help you with this. Because a lot of things I say, I don't mean to really be down on students or so forth, because a lot of this is solved by experience. They just haven't gotten to do enough of that kind of thing. So I'd say the students I know that have been successful are really the dedicated ones. This is, I have students with a lot of outside jobs, but one of their main jobs, I'm studying, I'm working hard. Just show up, right? That's the number one thing, is show up, ask questions. I'd say the main thing is the students who are motivated, dedicated, are the ones who are going to be successful. Because that's a lot of our job also, is you do it every day. You get up, read the archive, whatever it is you need to do every day. So this dedicated, application, I'd say. I don't have as much of an opinion on the high school. Like I said, I've seen, my daughter go through it. She's had AP Physics 1, AP Physics C. And I'm not sure about ordering with respect to the other sciences or so forth. Definitely it's helpful, certainly, to have the math sequencing correct. That's kind of what our boot camp is about, is in undergraduate physics, there are mathematical prerequisite barriers to get into Physics 1. You need to have had calculus, for example, right? And sometimes that can be a bit of an ask for students who may be interested in physics, but now it's going to take them some semesters, and they all can't afford to stay in school for that many semesters, right? So early intervention, like this boot camp, is part of the reason. So I think the math to physics sequencing is probably the most important there. I don't know about like with bio and chem and so forth.
Thank you.
So my understanding is that this course here for freshmen or those who are coming in do not have to take all of the preliminary math for the calculus?
At our university, we've talked to the math departments, and it can essentially be subbed out for like a pre-calculus rec. So they can start, if they do well in our class, they can start Calculus 1, and they can concurrently start Physics 1 with Calculus, because if they've gone through this class, they've seen essentially the calculus they will need for Physics 1.
So the engineering, so your students in a class is not all just physics?
Oh, no. Right now I have 31 students. There are 14 that are a mix of physics or physics and engineering. And then we have engineering technology students. We have, the other science students as well. So it's only about 50% typically are physics majors. So.
What is the percentage of students who do very well coming out of this class?
Students who do well in this class tend to also do very well in the Physics 1. I'll say that, yeah. Yes.
Hi, thank you. That was really great. Could you comment a bit on how you recruit for your boot camp program and how you make sure you get to the population that needs it?
Right, so all of our physics majors take it. They all take it. And then we just discussed with the other departments as well, like engineering technology, which we have an agreement with an engineering school, a UT Tyler, we have a sort of a 2-year physics, 2-year engineering program with them. So we have the recruitment then is also just at the high school level. You know, they come to the university, we have, you know, sort of freshman orientation or prospective student days, but also there's some outreach as well. You know, we have an observatory, we try to do outreach with those kind of things. So they're outreach and, yeah. But within the university, you know, we talked to the other departments. We partnered with math, for example, and like the engineering technology.
All right, maybe one more question. I think I'm a bit closer, so I'll just hand you my mic.
Hello. One of the things I've noticed is that students tend to remember the way they've been taught something the first time, if that makes sense. So it's sometimes hard, our job, what the middle school teachers have taught them, to unteach them.
Yes.
So I wonder what you see, like, as high school teachers, like, what are maybe some things that we're doing that make your job harder, like, when we're teaching them? Or if you also have, like, if you want to look at it more as a positive side, like, what could we be doing to make your job easier?
Right. Since this is recorded, maybe we can talk at lunch a little bit about it. But, yeah, I would be happy to go through some of the real detailed kind of things. Actually, that's one of the things we're trying to do with this text is, you know, common problems that we see. And we have lists of these, even down to, I don't know, you know, taking a square root of 2 sums and taking the sum of 2 square roots, these kind of things that, right. I wouldn't say that there's just one necessary thing that jumps out at me. Yeah. So, but yeah, it'd be great to chat. So.
Okay, so we're pretty far over time. We did start late, but maybe people are getting hungry. So let's hold the rest of the questions for lunch and go get some food. And thanks to all the speakers. Oh, wait, sorry. Wait, don't go anywhere. Wow, the self-control in this room is amazing. All right, before we go to lunch, I hate to cut off we'll thank the speakers again, but before we go to lunch, please, everyone in the audience who's a researcher, a postdoc, stand up so people know who to talk to. Who are here, especially the postdocs. A lot of more people have joined since this morning. So, yeah, these are our resident researchers that you can, or visitors that you can talk to, both. And, yeah, then again, let's thank the speakers, all the speakers for the great session.